Okay, so before we go on with more proof, let's think about a puzzle. So Roman dictator Julius Caesar used a special code, the ancient Roman cryptography, to encrypt his messages. And here's how he did it. And later on, people even made machines like the one you see here to encode and decode things in this kind of code. His code worked like this. Let's number the letters of the alphabet, A being 0, B being 1, and so on. Now, if you want to encode a message, you replace a letter by a letter which is 3 positions before that. So, for example, you would replace F by C, and X, well, X is the very, very first one, so you have to wrap around and go from the back. If you counted Z, then Y, and then you'll get A replaced by X. So think about this puzzle as we're talking about the material in the next lecture. And if you want to try your hand in ancient cryptography, try to decode this message. I'm not going to read it. It's not very pronounceable. But try to figure out what it says. Okay, so what was this about? In this lecture, we will be talking about some other class of things, modular arithmetic, and we will do a few definitions, a few theorems, and some proofs. Modular arithmetic is something that is very, very, very common in computer science, and the stuff that we are going to cover here, you will see later on in various applications. So let's first say what's modular arithmetic and what we're going to be talking about. So you might have seen expressions n mod d and operator mod. If you're doing Python programming, you would write it as n, then %sign, that d, and that operation will return you the remainder from dividing n by d, from integer division. But here, we are going to build, well, a predicate based, kind of loosely based on this definition, which is congruence mod d. So the difference in notation is very, very, very slight. For congruence, you have that equivalent sign instead of equality, and you put the mod d in parentheses. But the meaning is quite a bit different. So two numbers are congruent mod a third number, where all numbers are integers. It means that they have the same remainder when divided by d. And one theorem that we are going to use later on is the quotient remainder theorem. For any integer and some positive integer n and positive integer d, there are unique integers, let's call them q and r, such that n equals d times q plus r. And that r, moreover, is something that's positive or non-negative. It's greater than or equal to 0, but is strictly less than d. Again, this might be something that you've seen before, that you could write a number as a product plus the remainder. So, for example, you could write 16 as 3 times 5 plus 1, 11 as 2 times 4 plus 3, or 16 you alternatively can write as 4 times 4 plus 0. So in the first case, your d was 5, 3 times 5 plus 1. In the second case, your d was 4. And we are going to use that quotient remainder theorem as well as definition of congruence to prove some stuff. But before we go there, let's just play around with what congruent mean. let's just see some examples where, in order to figure out when two things are the same or different, we really need to see whether two things are congruent to each other, mod something or not. And the most basic example of congruence is calendars. So suppose you're writing a program or just trying to figure out whether 2 days of this, 2 dates in the same month fall on the same day of the week. You know what? If those two numbers are congruent to each other mod 7, then they do fall on the same day of the week. And if they're not congruent to each other mod 7, they're not on the same day of the week. So for example, in May 2017, all the Wednesdays had a date which had the remainder 3 when divided by, with integer division by 7. But in October of 2017, Wednesdays were all the dates that had the remainder 4 when divided by 7. Nevertheless, in both cases, all the Wednesdays in the same month were congruent mod 7. So another example, all the orange stickers or all stickers of the same color on the second picture are congruent mod 8. For example, orange stickers are all the numbers that have remainder 3 mod 8. So if you're not quite sure what congruence means, think of a calendar, think of those stickers. So maybe already seen how all of this can be useful in computer science. So not only it allows you to calculate things like are 2 days on the same day of the week, it's useful for some very, very important data structures that you will see later on, probably in 2002. And it has a very important role in cryptography, not just for Caesar, but for us nowadays as well. So the hashes, hash tables, those are very interesting data structures that allow you to store data coming from a very, very large range in fairly few memory locations. And usually the way you store it, if your data is random, is you calculate, say your data is some number, and you take that number mod some prime, and it pretty much guaranteed, if your data is really random, to give you pretty much a random place in your memory. So the chances of two pieces of data going into the same location are not that great. So this is a very important data structures used all over the place, and you will see in 2002. In cryptography, we use modular arithmetic for all sorts of checks and checksums. So for example, when you enter a credit card number, they can immediately figure out if this credit card number seems valid by computing some kind of operation on the digits and taking the result mod 10. So if you want to see exactly how it's done, you could Google for it. There is a formula, and this formula allows you to check very quickly whether the sequence of digits indeed might correspond to a specific credit card number. Of course, the would-be numbers that pass the check, they don't correspond to any specific credit card number right now because of other constraints, but at least it gives the system pretty good idea whether what you entered is some arbitrary sequence of digits or whether it could really be a credit card. And beyond that, modular arithmetic is used a lot in various crypto systems. We have gone a long way since Caesar's cipher, but a public key crypto system called RSA uses modular arithmetic a lot. So now that I hopefully convince you that modular arithmetic is an interesting thing that comes in computer science a lot, let's try to prove a theorem. And again, as we are proving the theorem, think about the steps and why various steps are true. So it's a pretty messy slide because I tried to get the whole thing on one slide, but let's go through it in pieces. So the theorem that we will be trying to prove is that if two numbers n and m, any two numbers n and m are congruent mod d, where d is some number, then there is an integer, let's call it k, such that one number is equal to another number plus d times that integer. Basically talking about if two numbers are congruent, then you could represent one of them by the other plus some multiple of whatever you're taking the mod of. And if you want again to write it down in language of logic, here's how you would write it. What are the quantifiers? N, m, and d are under universal quantifier. So for every x, y, z, and we want d to be greater than 0, z greater than 0, and x is congruent to y mod z. Here we didn't really write out the definition of it, but that's okay. Then there exists a y, so this will be our k, such that x is equal y plus, there exists a u, which will be our k, such that x is equal to y plus u times z. So let's do the proof. What's our first step? It's a universal statement, it's universal instantiation, and as before, assuming the premise means that we don't need to bother with talking about what happens when the part on the left side of the implication, z greater than 0 and x congruent to y mod z, is false. We know the thing is true, so we might as well just assume from the beginning that z is greater than 0 and x is congruent to y mod z. And we assume it for the specific numbers n, m, d that are names of those variables by universal instantiation. Okay, so what are we going to do then? We are going to refer to the quotient remainder theorem, which says that there are integers q1, and let's call the first quotient q1 and second quotient q2, and an integer r. We only need one r here because it's going to be the same, but if you want to be really, really proper, you would say there is r1 and r2, and r1 is equal to r2, such that n is equal to d times u1 plus r, and m is equal to d times q2 plus r. So again, there were lots of steps in this one line. There was an existential instantiation from the quotient remainder theorem, and there was a definition of congruence. So now we could just do algebra, n minus m, remainders cancel out, and we end up with d times an integer q1 minus q2. Now we are going to go backwards from instantiating things to generalizing things. We could give a name k to q1 minus q2. And now we got, again, using existential generalization, that since n equal m plus kd for k equal q1 minus q2, there is some u, which is q1 minus q2, such that n equals m plus u times d. That's great. And finally, our last step, always the same. Since n, m, and d were arbitrary integers, by universal generalization, we get that the statement is true for every n, m, and d, for every x, y, and z, satisfying that property. So here is a whole big proof on a single slide. And again, when you're reading it, think not that much about algebra. I'm quite certain that you could subtract one number from another number, but think about the steps. What was instantiated and why? Where was the theorem, quotient remainder theorem, used? How did the definition come? And when did we start generalizing things rather than instantiating them? So far, we looked at just one type of proof, the direct proof. That's when we start with a statement, then we do some algebra, apply some axioms, refer to some definitions with a few existential instantiations and generalizations, refer to some theorems, again with some instantiation generalizations, and finally we prove that what we started with is true. But in the next few lectures, I'm going to show you some other types of proofs which are slightly more involved. And the only difference is that instead of proving whatever statement under a universal quantifier is directly, we will look at the structure of that statement and maybe prove something equivalent to it. For example, it's contrapositive, to conclude that the original statement was true. So here we will be combining our logical equivalences with proofs as we've seen before in order to prove some more interesting things.